Hello everyone, I'm back with another series. Today with this video, we'll be starting off our series on stacks and queues. This particular video is going to be an introductory video wherein we are going to discuss the concept of stacks and queues, some basic operations on both of them, their use cases, time complexity, and finally the implementation. In the upcoming and subsequent videos, we'll be discussing some practice problems on both stacks and queues. So without any further ado, let's get started. So let's begin by discussing a normal array. When we talk about an array, we usually talk about declaration of the array and insertion or updation of elements in the array. Now, insertion at the back of the array is a O1 operation because the array is stored in a contiguous format in the memory. And while insertion, we know the exact position where the value is going to be inserted. And we can access and update the value at that position in just O1 time. Now, insertion at a particular index is a big O of n operation as all subsequent elements need to be shifted by one place. So updation is always a O1 operation given the index, again because we can calculate the exact position in the memory. Now stacks and queues are very close to arrays in the sense that they are linear data structures, and when we talk about stacks and queues, we are majorly concerned with insertion and deletion of elements. Both stacks and queues support insertion and deletion in a very specific fashion and are therefore used to solve a very specific and different use cases. So let's dive deeper into it. Now I'll first discuss queues and then we'll move to stack. Now we are very familiar with queues and the queue data structure exactly simulates the real life queue. Now let's assume that there's a queue of people in front of a food stand. So let's just make a queue and let's just number them 0, 1, 2, 3. So any sane person who would be coming into the queue would actually be joining the queue at the back or would be coming at the last spot in the queue. And in a queue, the person in the front is always served first. So the order for person 0 will be given first or will be fulfilled first, and person 0 will leave the queue. Similarly, and subsequently, the order for person 1 will be fulfilled, and so on. And every time, all the other people remaining in the queue will move one step forward. Now, if at any time a new person wants to join the queue, they will always join at the back. So this is exactly what a queue data structure offers. It is like an array where elements are inserted at the back and deleted from the front. Now this is also known as FIFO. FIFO stands for first in, first out. Because obviously any element that joins the queue first will also be removed first. Now in an array, insertion or deletion at first or last index is O1 operation. So both insertion and deletion in queues are also O1 operations. Now to understand a stack, let's assume a stack of coins. So let's say this is coin number 0, 1, 2, 3, and they are stacked on top of each other. Now again, someone who needs a coin and is sane would pick up a coin from the top. So what I'm trying to say here is that if anyone needs a coin, the first coin they'll pick up or the first element that will be removed from this stack will be the fourth coin. Now if anyone else wants a coin, they will pick up coin number 3. And if at any time a new coin needs to be added to the stack, that will also be added to the top. So let's say someone picked coin 4, coin 3. Now a coin 5 needs to be added. So it will be added on top of the stack and these two coins will actually get removed. So the stack would actually look something like this. 5 will be on top of 2. Also, we are assuming that all the coins in this stack are identical. So this behavior is simulated by the stack data structure. It is like an array where elements are added at the back and also removed from the back. Now this property is also known as the LIFO property, last in first out. That is the element which is inserted last will be removed first. So because the element inserted last will be on the top of all the other elements, so obviously it will be removed first. Now again insertion and deletion at back are O1 operations in an array, which implies insertion and deletion in stack are also O1 operations. Now till now we have been visualizing stacks and queues as arrays with insertion and deletion at back or front. But stacks and queues can also be implemented as a linked list. In a queue, the new node will be added at the back and nodes will be removed from the front, while in a stack, insertion and deletion of nodes happen at the end. Now, even if stacks and queues are implemented as linked list, our complexities for insertion and deletion would not change, given that we have stored the pointers to the head, the last node, which is the tail, and the second last node of the linked list. So if we have head, tail, and second last node, not the second node, the second last node, which will be pointing to tail. If we have these three pointers stored, then we can insert and delete in O1 time. Now that's it for the concept part. Let's try to implement stacks and queues and see how the implementation of the code looks like. We'll first start with stacks and then move on to queues. So a little bit of stack jargon. So let's say that we have a stack and currently there are four elements inserted into this stack. Then the last inserted element is referred to as the top element. So in this particular case, 3 is called the top element, and the pointer pointing to this element or the index of this particular element is referred to as top. So in this particular case, top will have a value of 3 because the index of this element is 3. Now, if we want to insert an element into the stack, what we simply do is increase the value of top by 1. So top will change to 4. So we increase the value by 1 and we insert the new element at the new index. So let's say we were inserting an element 4 into the stack. So 4 will be inserted at index 4. Now to delete an element from the stack, what we simply do is we decrease the pointer by 1. So in this particular case, when we are deleting, top will become 3. So what we have done, we were earlier at 3, then we inserted an element, top started pointing at 4th index, then after deletion, again top will start pointing at 3. So as you can see, we have not actually deleted the element, we have just stopped pointing it. Now if we want to again insert an element, so let's say that we want to insert an element 5, what we'll do, as earlier, we'll increase the value of top by 1. So top will become 4, and at this new index, which is 4th index, we will insert this new element. So 5 will be inserted at the 4th index. So our old value will get replaced with this new value 5. So even though we did not specifically delete the value, this kind of works because the value gets updated in the next insertion. So in stack, we mainly talk about four methods or operations. So first is the pop operation, then we have the push operation, then we have the top method, and then we have is empty. So the pop method is responsible for removing the top element from the stack. The push method is responsible for inserting a new element into the stack. The top method simply returns the value at this index, at the top index, or it simply returns the top element. And is empty returns a boolean based on whether the stack is empty or not. So let's look at an example. We'll do the following operation. So first operation is push 1, then push 2, then push 3, then top, then we'll do a pop, then again top, then we'll push 4, again a top, and then push 5. Now initially when we start, our top will be equal to -1 because the stack is empty and top is not pointing to any particular index. So as we discussed, while performing the first insertion operations, what we simply do, we increase the top by 1. So top will become equal to 0. Now our array is empty or there is no 0th cell. So we will add a new cell to our array. So we have added the 0th cell, and in this particular cell, we'll update the value 1. In the second insertion, again, we'll increase top by 1. So top will become 1. Now this cell currently does not exist in this array. So we'll add a new cell, and at this particular index we will update the value as 2, or we'll insert this value. Now again increase top by 1. Now again this cell does not exist in the array currently, so we'll add a new cell and insert our element into that cell. So 3 will be inserted here, 1 and 2 were already inserted. So this is how our array will look like. So we have already discussed that top method is responsible for returning the value of the top element. So currently top has a value of 2. So the top element is stored at index 2 and the value for that top element is 3. So this method will simply return 3. Now in pop method we have already discussed that we just reduce top by 1. So top will become equal to 1, and this is how our stack will look like. So there will be three indices, 1, 2, 3, and our top will be pointing to the first index. Now again we call top, so we have to return the element being referenced by the top variable, which is the element stored at index 1. So top method will return value 2. Now for push, again we have to increase the value of top by 1, so top becomes 2. Now this cell already exists in the array, so we do not add a new cell. What we simply do is that we replace the value in that cell with the new values. So our stack would look something like this, and top will be pointing to this particular index. Again, top will return the value being referenced by the top variable, which is 4. And push, so increase top by 1, top becomes 3. This cell does not exist in the stack, so we add a new cell, we update the value in that new cell, and this is how our stack looks like, and top will be pointing to this particular index. So now let's go through the code for stacks. So first of all, we have defined the class stack. This class is going to hold all the data members and the methods for stack. And as we discussed, there are going to be four methods. First is empty. Then we have top. Then we have push. And instead of pop, we have pull. So in some languages, pop is referred to as pull, while in some languages, we have the pop method. So pop and pull are the same things. Now for the data members, we have two data members. One is obviously top, which is always going to reference the top element or going to store the index of the top element. And then we have a storage space. So behind the scenes, we are actually using a vector as our storage space. Now we are going to delete and insert elements in a particular fashion so that this vector actually behaves as a stack. So we will always insert and delete from the top. So this vector is actually going to act like a stack. Now we have the default constructor. In default constructor, we just initialize our top variable. So it is initialized as -1. So we have already discussed when the stack is empty and there's no element in the stack, obviously top will not point to any element and its value will be -1. So first let's discuss the isEmpty method. So the best way to check if stack is empty or not is by checking the value stored in the top variable. So if there are any elements in the stack, top will have a non-negative value because top will be referencing the last element. Now if top is -1, that simply implies that the stack is empty. So that's what we have done. We in the if condition we have checked if top is equal to -1, then the stack is empty. Otherwise we return false, which implies the stack is not empty. Now we have the top method which returns the value of the element being referenced by the top variable. So first of all, we have called this helper method or isEmpty method to check if the stack is empty or not. So in case the stack is empty, we simply print that stack is empty and we cannot return any top variable and we return -1. But in case when stack is not empty, we simply return the value of the element being referenced by the top variable. Then we move on to the push method. So as we have discussed, we first increase the value of top by 1. Now after increasing the value of top by 1, we need to check whether this cell exists in the stack or not. So in case the top is greater than equal to the current stack size, which simply implies that this cell does not currently exist in this vector. So we add a new cell and we replace the value in that cell with the value that we need to insert. So by using pushback method, we have added a cell and put the value in that cell. In case the cell already exists in the stack, so we simply replace the value, the older value at that cell with the new value. Then we move on to the pop or the pull method. So while performing a pop or a pull, also we need to ensure that our stack is empty or not. If our stack is empty, we do not need to do anything and we simply print that the stack is empty. We do not need to perform any operation and we return from here. In case the stack is non-empty, then we need to perform our pop operation. So here what we are doing is that we are also printing the value that we are deleting. So that's why before decreasing the value of top, we have stored the value in a helper variable and then we simply print the value. So this is just an extra step, like it's not a conventional step that we do in a pop operation. It is simply for understanding. So in pop operation, the main thing that we need to do is simply decrease our top by 1. So now let's discuss the time complexity for the different operations. So isEmpty is going to be big of 1. We are simply checking the value stored in top variable, which is a constant operation. Again, in top as well, we are doing constant operation. So first we are checking if it is empty or not, which is a O1 operation itself. And then we are simply referencing the value. So accessing any element in the stack using index is a O1 operation in itself. So top method is also O1. Push is also O1 because again we are performing only constant operation. So we are increasing the value of top by 1, which is constant operation. Then we are doing a pushback in vector, which is a O1 operation, or we are replacing or updating the value using the index in a vector, which is also a O1 operation. So the overall complexity of push method is also O1. And as you might have guessed, the complexity of pull method is also O1, because is empty is a O1 operation, and then simply reducing the value of top by 1 is also a constant operation. So the overall complexity for pull method is also big O of 1. So now let's understand insertion and deletion on queues. Like the top and stack, we also maintain pointers and references in the queue, which are called front and rear. So why do we need two pointers? In stack, we performed insertion and deletion at the top, but in queue, insertion happens at the back, but deletion happens at the front. So we need two pointers, one for the ease of deletion and other for the ease of insertion. So let's say that we have four elements in the queue. One, two, three, four. So front will be pointing to the first element in the queue, and rear will be pointing to the last element in the queue. Now to delete, we just need to increment the front by 1. So if we want to delete an element from this queue, we'll increment the front by 1, and front will now start pointing at this index. So by doing this, we simply lose the track of the first element and start pointing to the second element. So it is essentially like deleting the first element of the queue. To insert, we increment the rear by 1 and add the element at the rear end. So as we used to do in stack, we used to increment the top. Here, if we want to insert, we increment the rear by 1. Now since there is no cell in the queue which is being pointed by the rear, so we have also need to add a new cell, and then we insert the element in this new cell. And that's how we take care of insertion and deletions. So there are four main methods in queue. One is front, other is enqueue, dequeue, and finally is empty. Now front is quite similar to the top method in stack. Front returns the element at the front of the queue. So the element which is being pointed or referenced by the front pointer. Enqueue inserts a new element into the queue. Dequeue removes the first element or deletes the first element of the queue. And is empty, again same as stack. It returns a boolean depending on whether the queue is empty or not. Let's quickly take a walkthrough of an example. So let's perform the following operations. Enqueue1, then enqueue2, then enqueue3, then front, then we perform a dequeue, then again front, then again we perform two dequeues, and then again an enqueue for 4. So again, as it was in the case of stack, both the pointers will be initialized as -1 because currently there is no front or there is no rear. So no index will be pointed by these pointers. So they are initialized as -1. So here first we need to insert 1. So as we used to do in stack, we used to increase the top by 1 and add the element. So in this case, we will increase the rear by 1. So rear will become 0, and we will add this element at 0. But right now the array is empty, there is no cell in the array, so we'll add the 0th cell and add this element at that particular cell. So the one extra thing that we need to do in case of a queue is that we need to check if front is -1 and we are inserting an element. So if front is -1 and we are inserting an element, that's a clear indication that this is the first element of the queue. So when we are inserting the first element or front is -1, we need to reinitialize front to 0. So this is one extra step that we need to do when we are inserting the first element. Now when we come at the second element, again we'll increase the rear by 1. Now this cell does not exist in this array already. So what we'll do, we'll add this cell and we will add the element at that particular cell, which is the first cell. Again increase the rear by 1. So rear becomes 2. Add the cell in the queue and add the element at that particular cell. Now we reach the front. So right now our queue looks something like this. There are three cells, 1 2 3, 0 1 2. Rear is pointing this particular cell 2, and we initialize front as 0. So front is pointing at this 0th index. So the first element in the queue is the one which is being pointed by the front pointer, which is right now 1 stored at 0th index. So this particular method which returns the first element in the queue will simply return 1, value 1. So now in DQ we've already discussed, we just need to increment front by 1. So when we increment front by 1, it stops pointing to the current element and it starts referencing the next element. So that's how we know that we have deleted this current element. So we are not actually deleting it, but we have just stopped pointing it or stopped tracking it, and which is kind of like deleting it. So after DQ, this is how our queue will look like. There's 1, 2, 3. Rear will be still pointing 3, but front will start pointing the first cell. So front will have a value of 1 and rear will have a value of 2. This is because in DQ we just increment front by 1. Now again we have a front method. So the current element being pointed by front is the element at index 1, which is 2. So our front method will simply return value 2. Now again DQ. So in DQ we increment front by 1. So this is how our array will look like, 1, 2, 3, and both rear and front will be pointing this particular element. Both rear and front will have a value 2, which is the second index. Now again we have a DQ. So in DQ, what we do is we increment the front by 1. So rear will be pointing here, but front will come here. So front will have a value 3 now. So now we try to analyze this situation carefully. We see that whenever front crosses rear, this implies that our queue is now empty because we have dequeued the last element as well. So when front becomes greater than rear, this is a clear indication that queue is now empty. So an extra step that we have to do in queue is that when front becomes greater than rear, we simply reinitialize both front and rear to -1, because now the queue is empty and we need to start all over again. So we reinitialize front to -1 and rear to -1. Now we have a enqueue method. So our front is -1, our rear is -1. So we simply increase rear by 1 because this is an enqueue method. So we will increase rear by 1. So a rear will become 0. And this is how our queue is right now. So there were 3 cells with values 1, 2, 3. Now our rear has become 0, so this value needs to be inserted at cell 0, and we already have that cell, so we do not add a new cell to the queue, and we just replace the value in 0th cell with the new value, which is 4. So this is how our queue will look like. Rear will be pointing to this particular element, and again we are inserting an element, and front is -1, which is a clear indication that we are inserting the first element of the queue. So as we have discussed already, when we are inserting the first element of the queue, we also need to reinitialize front to 0. So both rear and front now will be pointing to the 0th index and will have a value 0. Now let's quickly go through the code for the same. So again we have defined our queue class, which is basically going to contain all the data members and the member functions. So as we discussed, there are 4 member functions which are basically isEmpty, front, enqueue, and dequeue. So, and again we have a helper storage. So in this case also we are using vector, but we'll be inserting and deleting in a very particular fashion so that this vector simulates a queue. And then we have 2 helper variables or 2 pointers, which are front and rear, as we discussed in our example. So we have a default constructor. We are initializing both the pointers as -1 because right now the queue is empty and there's no element in the queue. So now coming to the isEmpty method. So when queue is empty initially, both front and rear are initialized as -1. Also, when we keep dequeuing elements and eventually the queue becomes empty, we have an extra step where we reinitialize both front as -1 and rear as -1. So we are kind of sure whenever the queue is empty, our front is definitely -1. So checking the value stored in front is a good way of checking whether the queue is empty or not. So we have done the same. We have put a if condition on front. So if front has a value -1, then we return true because then the queue is empty. Otherwise, we return false. Now we have the method front. So the first thing that we do is check if the queue is empty or not. If the queue is empty, there is definitely no element that can be returned as a front. So we simply print queue is empty and we return -1. In case the queue is not empty, then the front element is the element currently being pointed by front. And obviously front is nothing but the index of the front element. So we simply use the index to get the element in the vector and we return that element. Now coming to our second method, we have the enqueue method where we are going to insert a new element. So the main step that we do here, we increase rear by 1. Now if this cell already exists in the vector, we have to simply update the previous value. So if this cell already exists, we update the previous value. In case the cell does not exist, so that will be the case when rear will be greater than equal to the size of the vector. So in that case, where this cell does not already exist, we add a new cell and put the value in that new cell. And one extra step that we discussed that we need to perform is that when front is -1 and we are inserting. So this implies that we are inserting the first element in our queue. In that particular case, we need to specifically reinitialize front to 0. Now moving on to the last method, which is the dequeue method. So first thing that we check or first thing that we ensure is that our queue is not empty. In case our queue is empty, then we cannot delete any element and we simply return. But in case our queue is not empty, then we'll perform our operations. So again, like stack, here we are storing the element that we are going to delete. So we are storing its value in a helper variable just to print that this element is going to get deleted. So again, this is not a standard practice. This is something that we are doing just for the understanding sake. But the other logic is the main logic that definitely we need to do. So we have already discussed that in deletion, we increase the front by 1. We do a front plus plus or we increment it by 1. So in case if front is equal to rear and I increase the front by 1, so in case if these are equal and I increase the front, then front will become greater than rear for sure. And that is the case when the queue becomes empty, and we have already discussed that in that particular case we need to reinitialize front and rear as -1. So here what we have done simply, so instead of just increasing front and then checking if it becomes greater than rear, we have done if front is currently equal to the rear, then definitely by doing an increment it will become greater than rear. So in that case, this implies that this queue is going to become empty. So we have specifically reinitialized both rear and front as -1. Now the other case is when the queue is not becoming empty, which is a normal case. So in that case, front is less than rear. So in that particular case, we simply increment front by 1. Now coming to the time complexity, again the time complexity for all these methods is big O of 1, and the explanation for this is quite similar to the one given in stacks. So in all these methods we are performing constant time operations, and that's why the overall complexity for all these methods is big O of 1. If you want to analyze it, you can analyze it in a very similar way as we did it for stack, and you'll be able to conclude that the overall time complexity for all these methods is also big O of 1. Now you might think that stacks and queues do not have a lot to offer, but stacks and queues can be used to solve very complex problems, as we would see in the subsequent videos. Stacks and queues provide ordering to insertion and deletion, which comes in really handy while solving problems. For instance, the whole concept of recursion is based on stack. Depth first search and breadth first search are kind of the most widely used parsing or traversal algorithms in trees and graphs, and both DFS and BFS are almost entirely based on stack and queue respectively, and there are many more such algorithms. So also, as always, we do not have to actually implement stacks and queues before we can use it. All languages provide implementation of stacks and queues. So in C++, STL library provides stacks and queues and all the operations. So stacks can actually be declared using this kind of a syntax. So this is the template wherein you provide the data type, and this is how you declare a stack, and queue can also be declared something like this. Now STL also provides something known as a dequeue, which can be used both as stack and queue. So we would just need to be careful what set of operations we are using on dequeue. So while if we want to use dequeue as a stack, then we need to keep in mind that both insertion and deletion are happening at the back, and in the queue, deletion in the front and insertion at the back. So I hope that you've understood the concept of stacks and queues. I know that the main thing is to practice a lot of problems on stacks and queues, which would be really helpful. So in subsequent videos, we are actually going to take up some common and good problems on stacks and queues. So I'll see you in next video. Stay tuned. Until then, stay safe and keep learning. Bye bye.